did, it was Q learning, right? Mainly. I mean, we did SARSA also in the deep fashion, but that was less popular. Q learning, deep Q learning is the most popular one. Now, what do we do in all of these approaches? We just follow the main idea of value iteration, right? We're going to compute some sort of value, right? And that value is given by your network. That is a value network, mostly Q network, right? You look at that value, you decide for your action, right? This is the most basic version of deep reinforcement learning. This is the value-based version, right? And if you want to do value-based deep reinforcement learning, then you are fine as long as you don't want to deal with continuous actions. If you want to deal with continuous actions, then you're going to get into trouble. Now, why we could have trouble when we have continuous action, and this is happening in most practical scenarios, right? In robotics, well, the angle that one arm can choose is continuous, right? And in many other things, right? So realistic problems that we have are really continuous. And then the question you might ask me is that why it's a challenge, right? The key point is that when you want to do Q learning, you really need to maximize your Q values against the actions, right? So you want to find the action who is giving you the maximum Q value, right? And then when it's discrete, that's easy. You have a neural network, you just enumerate the output, right? And take the maximum one. But when it's continuous, what can you do, right? If it's continuous, this is a continuous function of A, right? And how you can show the continuous function of A by a neural network, right? That is the question, right? So that is the trouble. So if you have discrete case, you have one particular state, then for that particular state, you would say, okay, if I do action 1, I'm going to get this value, right? If I do action 2, I'm going to get this value, and so on. You can replace everything by a Q network, right? You would say all of it is a Q network, and every single output of this Q network is my action value, right? But the problem here is that if it is continuous, I mean, if you want to really do it, you need to, for example, if you want to do greeting, you need to greet your actions, right? And if the space of action is very large, then you need, for example, 10,000 greets, right? For example, right? Or even if the actions are much more, for example, a robot arm has multiple joints, right? And each of them is continuous, right? And then how many of that you can get, right? So say I just greet one joint with, I don't know, 100 greet points, right? If it has 10 joints only, then it's going to be 100 to power 10 greet points, right? And then you have a neural network with that much of outputs, right? You cannot do it. It's impossible, right? So this is not really possible to do that. You might ask me this question. You might ask me that why shouldn't we just think about one neural network? And this neural network really gives us, we give it the state in action as input, and it gives us the value of a state in action, right? That sounds feasible. Not this one, but that one sounds feasible, right? What do I mean? I mean that I have my Q network to be of this form, right? I would say this is the representation of my state in action, right? And now tell me what is the value for this state in action, right? That one is feasible because this has only one output, right? That I can do. But the problem then is that how you want to do just maximization here. Because in deep Q learning, you always need to find out the value for the maximum value among all actions, right? So this is the loop when you do Q learning, right? And in that one, you always have label here, right? And this label is looking into the maximum action, right? But this is not the only place where you are doing the maximization. Is there anywhere else that you do maximization? That one is indeed much more complicated. Do you see anywhere else in this loop, in this algorithm, that we are looking into the action with the maximum value? Yeah, go ahead.
The epsilon greedy update.
Yes, when you want to update, right? Because you want to find out epsilon greedy, right? You need to know what is the action which has maximum value, right? Again, you need to maximize it, right? So if you compare this one to the continuous one, it means that I don't think like I have this neural network, right? I just give the representation of my state in action, and then I want to just know what is the maximum one. I need to find the representation of the action which is maximizing, right? It's again the same problem in terms of complexity. You cannot solve it, right? I hope that I'm just conveying this message that this is not possible when your state is crazy large or is continuous, right? So since this is not possible, the question is that what should we do? Should we just limit our framework to discrete actions? And if the answer was yes, then we should say bye-bye today and then everything was over. But this is not really the case. And to be honest, this is not like after deep reinforcement learning. The idea of policy network and policy gradient is much older. So the base algorithm reinforced was proposed much earlier, like 1980s. Okay? So that idea was simply to handle this issue of continuous action. So as I said, in both update of your policy here in Q-learning and also taking the label, for both, in both of them, you need to know the action which is maximizing the value, and then this is a optimization problem which is quite complicated. So greeting does not work. One might tell me, okay, let me just find out the gradient with respect to the action, right? And try to just maximize it using, well, I have written here gradient descent, but I mean gradient ascent, right? Gradient descent of the negative one, okay? So just I use the gradient approach, like the gradient-based approach to maximize it. That one, if you do it naively, it's going to be the same complexity as the first one. If you do it intelligently, you're going to end up with policy networks, okay? So moral of the story, basic approaches are not going to work, but it's not impossible. Like, you can really do it. And the whole idea here is that you think about the problem differently. So just to give you a quick idea what it looks like, and it's going to explain what we're going to have in the next chapters. The main idea here is that, well, I have this network, and what does this network do for me? If I give it one representation of my state and action, right? If I give that one, then that network is going to give me the action value for that state in action, right? But the issue is that I cannot maximize it over A anymore, right? Now, if I have this network and it works fine right now, say I figure out a way to train this guy, right? And it works fine. Now, the only question is that if I look at one particular state, how do I know the action which is maximizing the value, right? If I do have another network, for example, another neural network, and that neural network looks at this state only. It doesn't care about the action, right? It just looks at this state where I am right now, and it's going to tell me that, well, I don't know what is the value, but I do know if you do this action, this particular action A star, then you're going to get the maximum value, right? So it's going to give me the action which is maximizing my value. Then I can get that action. I do have this state. I give both of them to this other network, and it's going to give me the maximum value, right? So I am going to get this term, this label once again, if I do have that extra network, right? Everybody clear? So now don't ask me how we can do it. This is what we're going to do rest of semester. But the question is, my point is that if those networks are there, and given that we're doing deep learning, we can always do that. So if those networks are there, does it work? Yes, it works, right? Now, look at that top network. What is that network? Can anyone tell me? It's a deep neural network, fine, but in terms of your RL framework, what component of RL framework that is? Yes? Policy, as you said. So that is basically a policy, right? But what kind of policy is that? Well, optimal, if it's really giving me the optimal one, but that is a deterministic policy, right? It's not a random policy, right? Obvious? So this guy is basically a deterministic policy, right? This guy is basically doing deterministic. It looks at your state, and it tells you what is the action which is giving you the maximum value. If it's right, then it's the deterministic optimal policy. If it's not right and it's doing a mistake, it's just a deterministic policy, right? Everybody's clear? So you have this policy network here. That is a policy network. Looks at your state, gives you the action. You have a value network here. It looks into your state and action, and then it gives you the value. You have the value you can update, right? And you keep on going. Everybody's clear? So this is like the most generic form of deep reinforcement learning. You have one network which is taking care of the policy. You have another network which is taking care of value, right? And up to this point, we only worked with this value, this Q network, right? We did not use the policy network. And if I told you initially, you would ask me, why should I have a policy network, right? If I know the optimal value, that's over. But the point is that in order to find out what is the optimal value, right, you need to know the optimal action indeed, right? And this is where the policy network is going to help you. So this is the most generic version. This is what we call it actor-critic approach, right? So you have a policy network. This is your agent, basically, right? It looks at the state. It decides to act. Once it acts, it gives it to a critic, which is the value network. That value network is going to tell you what is the value of the action you have done. And you can start interacting with each other till you converge, right? And this is the most robust form of deep reinforcement learning. So the whole purpose of this course is that at the end you have understanding of this one. And if you have understanding of this one, you can use it in practice. If you don't do actor critic, most practical scenarios, unless you want to just play basic computer games, is not working with basic Q learning. Okay? So in order to get here, we basically need to first understand what is a policy net, or how we can train a policy network, right? And this is what happens in the policy gradient method. So as I told you, this guy is basically a deterministic policy. You might tell me that, well, why should we think always about a deterministic policy, right? We could indeed have a general policy, right? And that general policy takes action value, for example, and takes state and action, the particular state, and tells me what is the probability of every single action, right? Now, this guy, even though you might say that, oh, I need to know A, you really don't need to know A anymore. Because you just give x of s to this, right? You just give the state to this. Then this is going to get tuned to the corresponding probability. You sample from it, you get one action, right? You basically do the same thing at the top one, but you do it with a deterministic approach, right? So if this guy is, for instance, a Gaussian distribution, which is triggered by your state. You give your state, then it's a Gaussian distribution, you just sample from it, right? And then this is going to give you one action, correct? Everybody's cool? So this is the policy network. Now, the thing that we do next is that we learn how we can train this policy network. And there, when we are training the policy network, we assume that we can somehow have access to the value of every pair. Now, you might tell me, how can I know it? Well, you can just do basic tabular estimate. This is what people used to do in old days. We can later do in the last chapter actor critic, meaning that we just get a value network as well, right? But before we get there, I try to just discuss this one alone, because that is much easier to understand. Like, you assume that you have this network, you get this state, you sample the action. Now you have a way, there is one way to give you the action value, right? And you forget about that. The only question is that how I can train this guy, right? Once you understand that one, the only piece left is that you replace that value guy with a value network. And that is going to complete the whole puzzle, okay? So that is the whole idea. So now, yeah. As I told you before, you might have asked me why we need a policy network, but basically, I guess now it's quite clear for you that policy network could really help, and this is what we're going to talk about. How we can train a policy network. This is basically policy gradient approach. Yeah? And to be honest, this is the most complicated part of the reinforcement learning. But don't worry, we have done our midterm, right? So there is no worries about that. So this is quite complicated. I try my best to break it down as simple as possible. I do understand at some point it's hard. I mean, even for me myself, first time it was very hard to follow some details. But no worries. I mean, once you get the idea and you use it, you gradually start to get feeling about that. Yeah, so that's the whole plan for the rest of it. So policy gradient is the next topic which we're going to talk about in the next chapter. And after that, we're going to talk about the action critic to just complete the whole puzzle, right? And then you have the whole, the complete network, which is just looking at the data and trying to train, to learn the optimal policy. Question on that? So my estimate was not that bad, right? That concludes that my